240 minus 170 is 70. So that's the delta lambda here in angle. And then in radian it's, okay, we have to find what is this in terms of how many pi this are. Because lambda in total is 2 pi. This 70 degrees amounts to 70 over 180 pi. So it's something like less than half pi. Okay? And there was also to calculate the phase speed of Kelvin waves. It was quite easy, right? So what is the number? I have 3.3 meter per second. What is it?
31.1 meter per second.
Okay, depends on what is G prime. Okay, so about 3 meter per second. And how long does it take to travel like a distance of 10,000 kilometers? If you calculate that, you will come to the conclusion it will take about 1 to 2 months to travel, which is about what we have seen in the exercise.
While calculating the reduced gravity, do you use the delta rho as one?
Delta rho?
Rather the fraction of the change in density over the density as 1%.
Yes. That's a number that is typically, that kind of results if you insert the equation of state for ocean and evaluate what is about a typical change of the density going from the warm to the cold state, then this is about the number that is found, and it's taken as a constant for all of our calculations. You multiply that by, in order to get G prime, you multiply that by G, and then you get 0.1 for the G. Oops. So last lecture we have discussed tropical waves. And now today we want to discuss the Ekman pumping in the atmosphere. You will start your the ocean dynamics course next week.
2 weeks.
In 2 weeks' time? Okay. So of course, then that will be repeated, what we discussed today. For the ocean it's even more important. In the atmosphere the main processes that are affected by friction are actually near the surface. But in the ocean it's both. At the top and at the bottom where frictional processes are important. And we have made use of this already. Actually in the last lecture also, when we imposed some kind of surface stress to drive ocean currents at the equator. Now this is the distribution of mean sea level pressure. So the numbers, the ISO lines here, 1000 hectopascal. This is what is called the Aleutian low. This is in winter. This is for winter, December, January, February. Mean sea level pressure and actually surface winds in this case. I just randomly picked the North Pacific. Could have taken any other stationary feature. Just But in principle, we have discussed this already last lecture, these kind of features. You see this, there is a low pressure, the Aleutian low, no? This stationary feature in the Pacific that drives strong westerly winds. In the Atlantic, we have a similar feature, which is the Icelandic low. I could have picked the Atlantic picture, but it doesn't really matter. The point we want to see here is that if we look at the surface winds and at the lines of constant pressure, first of all, we are quite happy that our geostrophic balance is valid to good approximation. The arrows here go along the lines of the constant pressure. See that, no? More or less. But there seems to be a systematic deviation. And the systematic deviation is that the winds seem to blow into the low pressure. Do you see that? The angle is always such that the wind has a slight component into the low pressure, systematically. So obviously you can guess what this is due to. The geostrophic balance close to the surface, if we go closer to the boundary layer, is disturbed by something systematically. And this is the surface friction. We have discussed this already for the trade winds, remember? Trade winds, they should blow, if the wind is purely geostrophic, from the east to the west. But they blow into the low pressure at the equator. Northeasterlies are the trade winds. The same here with the Aleutian low. So this effect becomes important in the atmosphere at the lowest layer, what we call atmospheric boundary layer, where we get closer to the surface, which induces friction. And actually, it's quite interesting, because quite obviously, the surface friction is in the end induced by molecular friction. It's really the molecular friction that takes away the energy from the system. But this knowledge is not very useful for us, because given what we can measure with reasonable size of our grid boxes, or model with models of a reasonable size of grid boxes, cannot be parameterized very well by the effect of molecular friction, because that effect would be valid on a very, very, very thin layer to the ground that we are not able to resolve with any measurement, with any model even. So what we actually can measure is the effect of turbulence on our mean resolvable flow. So if we are reasonably resolving like a boundary layer by, let's say, if we are close 100 meters height or even 10 meters height and in the horizontal 10-meter boxes, then it's not the molecular friction that is important, but they are the small turbulent eddies that take away momentum from our system, cascade them into smaller eddies, until really in the very end molecular friction can take over, when the eddies become so small that in the end molecular friction can take over. But those small eddies we are unable to describe if we have any reasonable resolution in a numerical model, or even in a, let's say, theoretical description of our system with a reasonable resolution. So we need to understand how these eddies act on our mean flow in order to do this. So this is well known as the energy cascade, that these eddies who act on the mean flow then become ever smaller eddies, until eddies are so small that molecular friction can really act on them. But those eddies we are not very well able to resolve anymore in any numerical model. So it's very useful to try to understand how to parameterize these kind of effects. So it's as with nearly all of this lecture course, of course boundary layer processes could fill a whole lecture course together. So the whole theory behind is a very sophisticated theory. We will just concentrate on some basic features that we will later on use in this course to understand mainly the vertical velocity that may be induced by this surface friction effects, which is called Ekman pumping in the end. So this is the main goal of this. It's not to present the whole theory of boundary layer processes, which can be very sophisticated. We are here dealing only with the momentum equation, but boundary layer processes obviously also affect the temperature. To evaluate the boundary layer depths is actually it's a whole theory behind this. What's the definition of the boundary layer depths? We will imply here a very, very simple definition, but in more sophisticated models of the atmospheric boundary layer, there can be very sophisticated definitions of what is actually the boundary layer depths. If you have a flight and you are going to land, you kind of feel the boundary layer, right? When the turbulence starts, you get closer to the ground, and then suddenly the boundary layer turbulence starts. You can actually feel it. We will have a very simplified view of this depth of the boundary layer, which we will introduce later in this course. But there are whole sophisticated theories. You could use a thermal definition. So the region, for example, where maybe the atmosphere is well mixed, and so potential temperature is nearly constant, you could use as a definition for the boundary layer height, for example. So one term that you will encounter when studying the atmospheric boundary layer is the Boussinesq approximation. It's an approximation that we have done already previously, which essentially led us to the shallow water equations in principle. In the boundary layer, it turns out the variations of density, if we are in the atmosphere, we know density is not constant at all. But if we stick very close to the lowest layer, the change of the density with height we can ignore for the time being. If we just stay to the lowest 500 or 1 kilometer, we can just say, okay, let's say density is close to constant as an approximation. And if we do that, then the pressure gradient force that we have in our momentum equation becomes easier, because then the density is just a constant. We don't have to worry about this anymore. We can just insert the number 1 here, 1 kilogram per cubic meters. In our what we call Euler equations, we have seen these many times already, of course, obviously look like this. Note that we have not included frictional forces here at all right now. We could have done that, but since we have mentioned already, they are not so important for the scales that we are interested in, so we simply leave them out. They will come back now, but for the time being we don't need this. We can write down this simply the Euler equations. And of course we have the hydrostatic equation always valid, but we don't need that in this course. Then we can also use, since we say density is nearly constant, we don't have to account for this density change neither in the vertical nor in the horizontal directions. It's small compared to the other variations that we have here. So we can use our incompressibility condition, the divergence-free condition. We have used this already many times. Now, this is the part of the Boussinesq approximation that we used in this course. There is a very important further ingredient which is related to the vertical equation of motion, which I think Adrian Tompkins may have used that in the atmospheric physics course in the last lecture, where you actually, if you want to resolve convection or boundary layer turbulence, you should also allow for deviations from the hydrostatic equations. Even though the hydrostatic equation is very good valid, but those small deviations that explain vertical motion in the boundary layer, turbulent vertical motion and due to instabilities in the boundary layer, may be dealt with in the Boussinesq approximation. So there's this You remember which term is it in the momentum equation that comes into play when we talk about the Boussinesq approximation? It's this buoyancy term, no? There's a vertical acceleration due to a buoyancy term. So some kind of density changes related to that we have to take into account. Even if we make in the other equations, we assume that the density is nearly a constant, but it's not exactly constant. But we don't have to deal with that here. This buoyancy term doesn't appear here. So another concept that you come across with when you study boundary layer processes and turbulence is what is called Reynolds averaging. So now we want to kind of reintroduce this additional frictional terms that we have ignored so far, but in an interesting way. We say, okay, whatever we do, however we describe our flow, we always think of resolving our flow in some measurable grid boxes on some measurable time intervals, which are much larger than the molecular scale actually on which friction would really act. So whatever we do is, if we have a numerical model or even a theoretical description of observations, we should decompose our flow into a resolved mean part and into a perturbation from that. So our flow, and we have done this several times already, may be decomposed into this part. Right now we don't even say that this should be small. You remember in our linearization, we have assumed that the perturbations are small with respect to the mean flow. Right now, not strictly necessary here. In fact, we don't make this assumption here. The only idea is that this is what we can either measure or model. So this could be a model resolved by a model grid box. This is our U bar that we can, for which we have in a discretized version of our boundary layer flow, for example, we have the result for. This is what we calculate. But this is subscript scale variations. We don't resolve this. Much too small. Or in a measurement campaign, we know our measurement can only be accurate and good on a certain length and time scale. So then this would be what we can measure actually in our measurements as the mean velocity and the mean velocity, and this would be perturbations from that we were not able to measure because they were so high frequency that we cannot measure them. In theory, these averages could be averages in space and in time. Let's think about the numerical model. It's very clear that this is the case. Because in the numerical model we have a spatial discretization and a time discretization. So in that case, this U bar would be U bar derived defined by a spatial grid box, which has some delta x here and a delta y, or delta z in our case, more relevant. And also, we know that this is valid for a certain time interval for which we integrate in time. And then these U primed are just perturbations that we know we cannot resolve. They could be zero. We are lucky. We just have laminar flow. But we know there could be something in this grid box that we simply haven't resolved. And it turns out in the boundary layer, these effects that we cannot resolve by our mean measurement or by our mean model grid box resolved flow are very important. So how can we derive this? So for the total derivative, which appears in our momentum equation, we can use a trick. You know that the total derivative can be expressed as d by dt plus u d by dx plus v d by dy plus w d by dz applied to this quantity A. But then, using our incompressibility condition, you can just add a 0 plus A times 0. This is a trick to use to reformulate the total derivative in this form here. Because if you add this and this, you can show that the total derivative just becomes equivalent to this term here. You call this, you know how this is called? You call this flux version of the total derivative. Sometimes, if you pose a model, it's convenient to have it formulated in this flux version instead of in this kind of formulation. They are equivalent, but we will see now that it can be useful to do this here. So this is the flux version of the total derivative. This version we can get only if we have assumed incompressibility. You know how the flux version looks like if we are a fully compressible flow. That will be and then not this one here. So this would be the divergence. This is the divergence of the, that's right, what we have there. But in the fully compressible flow, we would have the divergence of rho velocity and the quantity. And of course, you can use the continuity equation to show that this is an equivalent decomposition. This would be the flux version of a fully compressible flow. But you see, now you can see already what the problem will be. In this, we will now decompose this operator into mean parts, into fluctuations parts. That means the highest order fluctuations you can get from this product is a double A primed, U primed. But if we have this version, if we allow for compressible effects, in principle we can have triple products. So our treatment becomes much more complicated. One can do it. There's a whole formulation how to also to deal with these kind of weighted, we call this then weighted, density weighted averages. But it's not needed. It only complicates the analysis here. Let's keep it simple. So in principle, if we now apply the averaging operator to the total derivative, and we use, instead of this formulation here, we can write it down this way. This is because averages of perturbation quantities have to vanish. If we take the simple average of the U primed in our grid box, it should be 0, because that is what we resolved. It's a necessary condition here. It's not true, of course, for product of prime quantities, but it's true for the prime quantities themselves, like we did with our perturbation in our perturbation theory. So if we calculate the average of a product, decompose it, then we get just the mean, the product of the mean, plus the average of the perturbations from it. If we apply this now to our momentum equation, the only nonlinear term here, remember the density in this calculation we keep as a constant, otherwise there would be a nonlinear term here, which in the Boussinesq approximation for the vertical velocity is actually treated and relevant, but here we don't consider this. We get these additional terms. d by dx u primed by dx, d by dy u primed v primed, and d by dz u primed w primed. So if you want to formalize this, this would be of course the three-dimensional divergence operator applied to u primed and the full three-dimensional velocity convergence of that term. So it's a full three-dimensional divergence here. But in this operator here, we only treat terms that can be resolved by our mean state quantities. That was the idea, to keep the first part of these terms, they are all terms that we can resolve. We can measure them and we can integrate them in our numerical model. And these are terms we cannot resolve. We don't know what to do with them. We can set them to 0 and see if we find a nice solution. But that's an assumption that is probably good for the troposphere above the boundary layer, but maybe not good for the boundary layer. Experience shows. So for our divergence-free equation, it's a linear equation. If we apply the averaging operator, we just get the mean quantities. The perturbation quantities just get out. So we have now this set of equations. But we have a big problem here, because we have these quantities here that we don't know what to do with them. As I said before, we may say they are 0, but that may be not a very good approximation. So this problem is called closure problem. We have a set of equations for our mean quantities, but we have, if we think that these additional effects of this unresolved flow on our mean flow is important, then we have a closure problem. We have to parameterize these terms. One parameterization could be to say, oh, they're 0. Let's see what we get. Then we are back to our original equation where we don't have applied any averaging operator in principle. So what do we do? This is a big problem in turbulence theory. It's called the closure problem. Because we have to do something. Otherwise we cannot go on now. We don't know what to do with this. They can be important, they cannot be important, we don't know. So there are tons of theory how to try to close this system. There is a way, actually, you can derive equations for these terms here, prognostic equations for these terms here. You can derive an equation for d by dt, a prognostic equation for example, one term that could be relevant is u prime w prime. You can do this. If you're carefully going into the Navier-Stokes equations, you can derive an equation for this. The problem is that if you do that, on the right-hand side there will be terms that are dependent on these, but there are also triple products. Could be something like this. So there are triple products of flux terms, where you again, if you just have a prognostic equation for this, and here's a bar, for this quantity here, again, you have to parameterize here. So there's never an end to the story. That's the result of the nonlinearity property of our equations. Even if you derive equations for, this could be, for example, sometimes it's called turbulent kinetic energy closure. Some ocean models and some atmospheric models have such a closure. They postpone the problem to a later stage, because now you have to parameterize these processes. Some people believe it's better, so you write down the prognostic equations for the second order variations, but then you have to parameterize this. And if you derive an equation for this, you get a quadruple fluctuations. So there is a never an end to the story. At some point you have to parameterize. We are keeping things very simple here. We say, okay, anyway, in principle the problem cannot be closed unless we make assumptions. There's no theoretical closure to this. Any assumption that is valid here could also be valid there. So we make a simple assumption. We say we want to parameterize these quantities. And the most kind of well-known parameterization is called flux gradient theory. So we know what molecular friction does. It tries to reduce gradients. So if we have a change in velocity, what our molecular friction tries to do is to bring two fluids to the same kind of velocity. Or if we have to the ground, it tries to bring the fluid to a state where there's no flow at all, close to the boundary. It tries to reduce gradients. That's what our molecular friction does. We say, okay, let's assume our turbulent eddies act in exactly the same way on our mean flow. So we could, for example, say that we could parameterize the U prime W prime and the V prime W prime, which turn out to be our most important terms, by this formulation here. We have always to try to parameterize them as a function of the mean resolved flow. Otherwise we haven't gained anything. So U prime W prime bar, we want to have a function of U bar, V bar, whatever. Any mean state quantities. Could also depend on explicitly on height and on X and on Y, which could be complicated, but if we have such a formulation that doesn't depend on any prime quantities, we can evaluate what this should be. The simplest version of a parameterization is what we just mentioned, this flux gradient theory, where we say, okay, the action of these eddies, of these eddy fluxes, should be that they try to reduce gradients in the mean flow. So one parameterization would be simply to say, okay, this is the coefficient times du by dz. If du by dz is 0, then this additional term becomes 0. Then the turbulence has reached its final aim. It has reduced the gradients in our mean flow system. With this parameterization, we can close the system. However, we have another problem now. This Km, this exchange coefficient, for we call it Km here, we don't know really what this is. It's not the molecular. For molecular friction, you can derive from basic theory what the frictional coefficient should be. But in our theory, we have just assumed it's some value here. We have no idea. We will later use some indirect ways to guess what is a typical value of this. But this could be measured, of course. Now you can go ahead, take measurements in the boundary layer of this eddy covariances. You try, okay, let's say we try to measure very high, you don't measure molecular friction, but you try to measure this eddy covariances by improving your resolution and relate this to a mean flow. And then by relating these two, you can evaluate first of all, you could evaluate if this condition is more or less fulfilled. If there's a linear relationship, let's say, between these eddies and the mean flow gradient, and you could evaluate what is this Km value. Of course, in measurement studies of the atmospheric boundary layer, this has been done. So these values have been evaluated. But then they may depend on your exact location where you are. So it's not an easy thing, but so many weather forecasting models probably use formulations to close the equations in the boundary layer as simple as this simple flux gradient formulation. But then there could be more complicated formulations of this exchange coefficient, which sometimes is a function of the vertical coordinate z, or could be a function of the stability of the atmosphere, of many other things. But in order to have a first order understanding what friction does, we don't have to take this into account. So with this, we can try to solve the equations in what we call the Ekman layer. So the Ekman layer would be the layer not very close to the surface, but close enough to the surface, and that extends up to the free atmosphere, where we assume actually that we have geostrophic equilibrium. Good approximation of geostrophic equilibrium. So we want to understand now what our friction does in order to disturb this geostrophic equilibrium that we have in the free, nearly in the free atmosphere. It's not exact, of course, because even in the free atmosphere, we know we are not in exact geostrophic equilibrium, but we are in a good approximation in a geostrophic equilibrium, about to 10%. But in the boundary layer, this equilibrium is even further disturbed, because we have this, what turns out to be very, very relevant and strong frictional processes induced by the turbulent eddies. So that means what we want to do is that we want to replace what we can do, we can replace our pressure gradient force by the geostrophic wind that we can measure in the upper layers. So the geostrophic wind is just, we assume that's the wind that you can measure at the top of our boundary layer. We assume that's in geostrophic balance. So we can simply get rid of this pressure gradient force and write the equations in this form. Now, in this case, we have done some more approximations actually. First of all, we have dropped the bars, because now all the quantities are average quantities. The prime quantities do not appear anymore, so we can simply drop the bars. Let's get rid of them, make it simpler. Secondly, we have ignored the vertical advection term, because in principle in our equations there were still vertical advection terms of the mean flow. This term here. We've assumed this term. We could treat it, but it would make our theoretical treatment much more complicated. Maybe the system wouldn't be closed. But in principle, in reality, it could be there. So what we really try to do is, what is just the first order perturbation of our boundary layer in terms of adding this effect of turbulent eddies, and not to take into account all kind of other terms that could also be relevant in principle, like this advection term here. But it's justified to assume that this is much smaller than all the other terms that we are considering. The same with these horizontal terms, horizontal advection terms. In boundary layer theory, actually, this is called the assumption of horizontal homogeneity. So we assume that our flow is just not changing in the horizontal direction. It's an assumption, so you can find a solution. Otherwise the solution could be much more complicated, and we were not able to do it anymore analytically, but we would have to do it numerically. We could do it numerically. In fact, in models this is done. These assumptions are not done. You just insert the frictional term in the boundary layer, and then the model calculates the effects on the mean flow. But if we want to have an analytical treatment, it's very useful to have this horizontal homogeneity assumption, which kind of removes these effects here. No changes in the horizontal direction. We look only at changes in the vertical direction. We assume that in the horizontal direction, things do not change for the time being. But to ignore this term is a real approximation. But we have, in the past, we have ignored this term always when we assume, for example, geostrophic balance and so on. We have ignored all these terms. So this is kind of the first, the first order effect, to try to understand the first order effect of friction of our mean flow. Because if you assume now that we are now a little bit higher up, then if we assume that our friction is zero, this effect is zero, then the solution of this equation is just this geostrophic wind. V is equal to Vg and U is equal to Ug. So our interpretation is that we try to understand what is the effect of friction in perturbing our geostrophic balance indeed. This is the only thing we want to understand in this lecture here. What is the effect of our turbulent eddies in perturbing our geostrophic balance? Because that would be the solution otherwise. Very simple solution. If f is not equal to 0, v equals vg and u equals ug. The equator is another problem. We exclude the equator right now here. Next lecture we will see how it's not absolutely necessary, but in most of the classical treatment of the subject, we think f is different from 0.
But in this equation, v without the g is just the Eulerian velocity, or what it is?
This here is just the velocity, yes. The velocity that we can measure or describe in the boundary layer.
Okay.
So that will vary.
Okay.
Whereas we assume that the geostrophic wind
Not very-
is not varying.
Okay.
It's just the velocity that we can measure at the upper end of our system and that we treat as constant. So that in fact, with that we assume that our pressure gradient is constant in the boundary layer. We will make this assumption later, actually. At the moment we haven't made this assumption, but we will make this assumption later. That would be equivalent to the geostrophic wind not changing with height, means that we assume that we don't have any baroclinicity. Our temperature, large field temperature field, should be also homogeneous. But maybe for this treatment here again, it's a useful assumption. In reality, it may not be exact again. But to understand the first order effects on how frictional turbulence effects. Hi. I hope you can follow what we are talking about now. We are close to an end actually already, but not so close. Some things we are still to discuss. So we have discussed what is the effect of friction on our flow. And it turned out that we can, what our point of view is, what we want to understand in this lecture is how frictional effects, and we don't mean by that molecular friction, but turbulent, the action of turbulent eddies on the mean flow, may disturb our geostrophic balance in the free atmosphere. So this would be only valid at the lower, if we go to the lower layer of the atmosphere, what we call atmospheric boundary layer. There we think that frictional effects that we have parameterized in this way could be important. We've assumed that our flow is horizontal homogeneous, so no changes in the horizontal direction here. So with this we can use a trick to reformulate this equation. Again, now we use the condition that if these properties are constant, so the pressure gradient or the geostrophic wind, they're constant in the boundary layer. Could be an approximation if it's not exact the case. Then we can introduce this new variable U star and V star, which are just these deviations here from the geostrophic wind, and reformulate this equation in this form here. Km d by d z square U star V star plus then a matrix applied to U star V star equals to 0. And this matrix is just the Coriolis. It's antisymmetric Coriolis matrix. Now we want to find a solution. We are kind of very lucky because we have derived, using some approximations, but in principle we have derived a set of linear equations with constant coefficients, because we will assume for our treatment also that this exchange coefficient is constant. Then we can use our linear theory again. We have a system of linear equations with constant coefficients, so we know that exponentials or sine and cosine should be solutions of this equation. So we can try, or what happens if we assume solutions of this type. And then any solutions could be superimposed by Fourier series using what we find now in our characteristic equation. So we try solutions of this type. Our solution should oscillate in the vertical direction with amplitudes A and B. So we insert this here. And we find what we found many times before. We get a system of two equations for our two amplitudes. Again, if we assume that our two amplitudes should be different from 0, then we know the only way that this is has a solution is that the determinant of this matrix is equal to 0. So this times this minus this times this. We get to this equation here. Quite simple. The only problematic is that is to the m, to the vertical wave number, to the power of 4. So there are many roots here. If you calculate the solution, you find, of course, that there are four roots, 4 solutions. And an additional complication is that we get the I, not only the I, but the square root of I in these roots. But we have this identity here that the square root of I can be expressed as 1 plus I over square root of 2. You can evaluate this by squaring it. Actually, see that this is the case. Then you insert this here, and you, of course, gain nothing, not much. Still, we have 4 solutions. Okay, it's just a little bit tedious mathematical treatments. Consider also that we have boundary conditions. Boundary conditions are very important here. So the boundary conditions are that our wind goes to the geostrophic wind if we go up, but the wind should go to 0 if we are close to the surface. These are our boundary conditions. Kind of no slip boundary conditions at the surface. But you can see that this idea that the wind should go to the geostrophic wind means that that the wind solution in the U star and V star should go to 0 if we go up, because that was the deviation from the geostrophic wind. That means we cannot allow the solutions that grow actually in the vertical directions, which are 2 of them. So we can ignore them. So the solutions that we can exclude because of this is the one that grow in the vertical direction, which are M2 and M4. You can show this by inserting the values. So the only solutions that survive with the conditions that we have decaying solution in the vertical are M1 and M3 from the 4 solutions. But there are also, it turns out, if you insert them back into the initial equations, that it turns that corresponding to these eigenvalues, there are eigenvectors that are not independent. So that means we can just pick one of them. We can just pick one of the solutions, and we have found already all the solutions. So in our case, we pick M1. We insert this M1 into the equation. So we replace e to the power of I m z by its cosine plus I sine expression, so this usual expansion of this. Yeah, inserting for the solution for M1, because M1 contained both the real part and the imaginary part. So the imaginary part gives the damping in the vertical, and the real part here gives the oscillation in the vertical. And we still have to assume that this quantity A, this factor A, is a complex number. But in the end, we are interested only in real solutions. So if we look for if we insert this here and look for the real part of the solutions, we find this is the full solution here. But now we can try to determine C and B in this case by our boundary conditions. So if we look at Z equal to 0, then we know that U star should be minus UG, and if you insert this here, at Z equal to 0, for example, this is 0. So if this is minus UG, then you can evaluate what B should be minus UG. And the same we have for this equation here. There, this term vanishes, and you can evaluate that C is actually minus Vg. So you can insert these two parameters here, and we have found the solution. Is the solution here that has a oscillating part in the vertical direction and a decaying part in the vertical direction. The decaying part is this, and oscillating part is this. So if we now see if the boundary conditions are fulfilled, so z equal to 0, what happens? This term vanishes, this becomes minus 1, this is 0, this is 1, e to the minus 0 is 1. So this is ug minus ug is 0. So at the bottom we are okay. The same is true for v, no? If this goes away as z equals 0, this becomes 1. So we have Vg minus Vg 0. At the top, if we go to infinity, very high, then this becomes 0. So this whole factor becomes 0, and we get that our wind is a geostrophic wind. So the bound conditions are fulfilled with this solution. And actually it will be an exercise for you to show that inserting this back in the original differential equation, this is a solution of the differential equations. It's always easier to do this, to dream a solution and to insert it back in the original equation to show that it's a solution. Okay, so how does this solution look like? It's shown as an example here in what we call this is phase space diagram between, so on the x-axis here is the u velocity, on the meridional axis, on the y-axis here is the v velocity. We start at 0 and then we change the altitude and we draw our solution values and we see what is the outcome is the spiral, which we call Ekman spiral. So at the bottom, 0 wind. But then even though in this case the geostrophic V wind was set to 0, there's only geostrophic U wind. But still, in the boundary layer, due to the rotation, we get a substantial meridional wind component, and then that exponentially goes to 0. This is the theoretical solution, and it's compared with the real measurement. You see, okay, something is similar, but other things are very, very difficult to resolve. This part close to the boundary, but then as we go up, the solution seems to fulfill more levels. I doubt that anybody can show these oscillations if we go to high levels, but it's only a part of the theoretical treatment. So this is nice, we have found a solution, but we are not yet there. So we are using now one feature of the solutions. We want to define what could be a suitable value of the exchange coefficient Km, because Km determines our gamma. F, we know where we are. At the moment we cannot be at the equator, but for this treatment here, but as soon as we are a little bit away from equator, 100 kilometers or something like this, we could already evaluate what is the F that we have to insert here. So we want to have a guess what is our exchange coefficient, which then determines our gamma. Either we measure it, and people have measured it, but one other way to do it here, to define some kind of depth of the boundary layer. So if we define the depth of the boundary layer, which is the height where the wind for the first time becomes parallel to the geostrophic wind. It's not exactly like the geostrophic wind, but where it becomes parallel to the geostrophic wind. If you insert this here, that will be the case for pi over gamma, because then this becomes 0 and this becomes 0. So the wind will be parallel to the geostrophic wind, because we have only here the U component and here only the V component surviving. there will be a small change. But by that time, the exponential part here has made decline this contribution already so much that we are very nearly already at the geostrophic wind. So we can see this here in this theoretical treatment. We will look for this point. We want to know what's happening if we take the theoretical solution. We look for the first point when we get parallel to the geostrophic wind, and then there are some small variations here. So we make only a small mistake here. We can use this trick actually to estimate, okay, since we may be able to measure what are typical heights of this boundary layer better than the actual coefficient Km, we can say, okay, our experience shows us that the mean height of the boundary layer, we can maybe measure that by our plane experiment. We land and we see where the turbulence starts. It's about typically 1 kilometer. If we insert this value in this equation here, we find that the typical value for us to be used for large-scale models, let's say, of this exchange coefficient would be 5 meters square over second. This is just an order of magnitude for us. In more sophisticated theories, you would have more. You probably would take values from this that are derived from measurements, or honestly speaking, in models these are sometimes also used as tuning parameters. So you try to vary within the possible range of these parameters. You try to vary them to get your model reproduce the mean climate. For example, the flow speeds at the lowest model levels that are closest to the observations. Because these numbers here will never be known, since they cannot be derived from molecular principles. They will never be known more to about 10% or to even 20% if we are lucky. In some cases even worse than this. So there's always some uncertainty in these exchange coefficients that are used in numerical models. Even if you use a higher order turbulence kinetic energy closure, there will be parameters that cannot be derived from first order, from first principles, and therefore they have some uncertainty. So for us, this is just an order of magnitude. So what we really want to do is now to see, we know that our geostrophic wind is without divergence. And that means if we use our incompressible condition, that there is no vertical velocity in principle. Divergence free. But in the boundary layer that's not the case. Intuitively we have seen that already. The wind, in the trade wind regions, they diverge where we have the subtropical high pressure systems, and they converge where we have on the equator. So there are effects of the friction. In our Aleutian low, what would happen? We can guess that. Intuitively, it's very clear to us. So we see that there's this wind component into the low pressure. So what will happen in the end is that the wind will converge where we have the low pressure, and due to the incompressibility condition will rise. This is important because it's one of the mechanisms important to create vertical velocity. Why is vertical velocity such an important quantity? Because it is very much related to rainfall. You have derived this in Adrian Tompkins' lecture. Whenever there is a rising motion, at some point that will lead to condensation. Right? It will lead earlier to condensation if the air is very or almost saturated. But even if the air is far from saturated, if you lift a parcel high enough, at some point there will be condensation. That is because as the parcel is lifted, it cools off. As long as it's not saturated, it cools off according to the the adiabatic condition. And this cooling off is reducing the water pressure, the partial water pressure so much that at some point there will be saturation in any lifted parcel. So vertical velocity is very important for us to understand where we may get rainfall responses, for example, remotely to an El Niño event. Or if we have flow, what will be the rainfall response in some regions? Because if we know vertical velocity, we may estimate regions where we get lifting and therefore rainfall, or we get sinking motion and therefore lack of rainfall. Ekman pumping is one process. So in this region we would expect convergent rising motion, convergent motion, rising motion, and probably increased rainfall. And this is obviously using our solutions, what we can calculate. We have now our solutions for in our Ekman spiral. We can calculate the divergence of this. The divergence, this is a simple calculation. You can calculate this, contains these two terms. One contains the divergence of the geostrophic wind, which is 0 for our definition, because we assume that the Coriolis parameter was a constant. So the geostrophic wind is divergence free. The first term here is out. Remains the second term, which is proportional to the vorticity of the mean flow. It's an interesting quantity. The vorticity of our geostrophic flow determines the magnitude of the divergence in the boundary layer due to friction. So whenever, yes?
I ask about this diagram. It's also related to vorticity. We know that, if, for example, the spiraling wind reduces, it's supposed to flow at a faster rate. But from here, the arrows show the flow is a bit relaxed in velocity.
I'm not sure I understand what you mean.
I don't know if what I'm saying is, I mean, is the length of the arrow showing the speed with which the wind is moving.
Yes.
But if you get close here, I expect because of vorticity conservation, then the flow is supposed to flow faster.
Flow fast. I think the speed should probably scale more with the pressure gradient, no? So you have to look, if you want to know UG, you should look for the gradient of the pressure. So where the isolines of constant pressure, where they're very narrow, you find the strongest speeds, which may not be at the center, but in other regions, which I think is the case. Yes. So you can make it much simpler and say, okay, when I want to know where the wind speed is very large, I should look for strong gradient in the pressure, strong changes in the pressure. So the result is that a geostrophic vorticity, any rotational flow, doesn't even have to be really, you don't have to see it that it's rotational, but it could just be a shear flow without rotation at all, that you don't see any rotation at all, but just a flow, for example, a completely zonal flow that has a du by dy would have vorticity, because vorticity is not only rotation. So vorticity could be simply a dug by dy, and then vg if vg is 0. So if you have simply a flow that is zonal and that varies in the meridian direction, that contains vorticity. And that is perfectly fine to create convergence in the Ekman layer. But if we have really a closed circle flow, like we have rotational flow in this way, like we have in our Aleutian low, that's perfectly fine too, of course. That's vorticity, of course, what we see here. So the final expression is this. So we get an interesting relation between geostrophic vorticity and divergent wind in the boundary layer. And that expression is this here. Now if you evaluate no, here not yet, this is our expression. Now our final idea is to evaluate what could be by this divergence, what could be the vertical velocity at the top of the boundary layer. That could be useful to understand, for example, to trigger convection, to trigger rainfall just because of this vertical velocity. Could be interesting to understand this. So we want to do this. So we integrate the divergence. We have the divergence precondition. So the horizontal divergence, if we integrate that from zero to the depths of the boundary layer, we can evaluate what is the vertical velocity at the height of the boundary layer, assuming that it's 0 at the bottom, which is, of course, a valid assumption, a proper boundary condition. If we do this, very easy to integrate, we get to this expression here. Again, the vertical velocity at the top of the boundary layer is directly proportional to the vorticity of the geostrophic flow. Whenever we have vorticity in our geostrophic flow, we get vertical velocity, positive or negative, depending on the sign of the vorticity. So when the vorticity is positive, we get rising motion in the atmosphere. When the vorticity is negative, we get sinking motion. We also, for simplicity here, we don't have to do this if we want to be more exact, but we can ignore this e to the power of minus pi, because it's about 0.1. So in order to be, since we have made so many assumptions here, we don't have to do it. We could just make a factor here that is 0.9 or whatever. But in order for simplicity, we can say, okay, this is small compared to 1. So our final expression would be this. The vertical velocity, anyway, even when you don't, the following statement is true. We don't do this. The vertical velocity is proportional to the vorticity of the geostrophic wind. And this is, we can do a very simple calculation that shows that this is actually relevant. Because it may turn out to be not relevant. We have a vertical velocity, but perhaps for climate studies, it's not a relevant vertical velocity. We can just ignore it. But it turns out it's not the case. So we can compare this. We have looked at this assumption already many times, that when we have a convection okay, this was omega. That any convection that we have, for example, in an El Niño case, that is creating convective heating in the atmosphere, should be compensated in the tropical regions to first order by the adiabatic lifting. If that's the case, we can relate what is the typical vertical velocity, for example, in a heating case. If we insert a typical heating, this could be relevant. Maybe El Niño would have more than this, okay? But this would be a typical heating rate for a weakish El Niño. Maybe not a 1 degree or 2 degree, but a half a degree El Niño or something like this. Then, if we use typical stability parameters for the atmosphere, that would give us a vertical velocity that is very much the same as the one that we can calculate by inserting some kind of typical vorticity in the atmosphere with the typical boundary layer depths and the resulting typical gamma coefficient, which would be a 2 times 10 to the minus 3 meter per second. So the vertical velocity that our Ekman pumping induces is comparable to the vertical velocity a kind of weakish El Nino event would create through compensating vertical motion due to the heating. So it is a relevant mechanism to create vertical velocity. Just we will discuss in the next lecture in many more details what are the consequences of this. I just want to highlight you one consequence, for example. If you look at, we have said, okay, if there's an El Nino event, we are interested in El Nino teleconnections. Because, okay, El Nino may be only in the Pacific, but then it may influence climate around the world. For example, we have said that in the atmosphere, the response can be very well estimated by this kind of Gill response, with this gyres, Rossby gyres here, and the Kelvin wave side of the response to the east. So this was our estimated atmospheric response, let's say at the surface to a heating. But the heating is only here. So in this region here, we would have vertical motion, rising motion because of this effect here. We have the heating that is compensated by rising motion. The Gill model itself does not include frictional processes. So the Gill model, the rising motion here is compensated by sinking motion everywhere else. If you look at the paper, that's the outcome. But that's not the case in the real world. But the model doesn't include the Ekman friction or any frictional processes. Apart from this Rayleigh damping, which was everywhere in the model. So what we get are these gyres, for example. The cyclonic gyre here and the cyclonic gyre here. From our experience now, we can see this is geostrophic wind actually. Even if we are close to the equator, but our fields are in a very good, this beta Y terms, they were all in geostrophic, very good in geostrophic balance. You can see this here, the pressure lines and wind vectors, they are in good geostrophic balance. So that means we have geostrophic vorticity here. According to our calculation, this is cyclonic vorticity, we should get rising motion. We should expect rising motion in these gyres here. So we should expect, of course, increased rainfall here because we have that is what we have imposed, heating somewhere here. But we would also expect increased rainfall in these two Rossby gyres. On the contrary, look at this. Here we have du, so vorticity. So the easy part on the eastern side here is that it's determined by Kelvin waves. So V is 0, but we have du by dy. So vorticity, geostrophic vorticity, will equal to minus du by dy. So what is happening? U is negative here and is decreasing with y. So that means u itself is negative, but it's decreasing, so this whole term would be negative. So on the eastern side, we get negative vorticity, if we exclude the equator, off the equator, negative vorticity, negative geostrophic vorticity. So what we expect on the eastern side of a heating anomaly, in the subtropical regions, let's say, is a decrease of rainfall as response to ENSO, because the Ekman pumping would cause here sinking motion, whereas it causes rising motion here. So this is one of the mechanisms how El Nino, outside the region where El Nino is actually happening, can cause rainfall responses, just looking at our simple Gill model. Yeah, so in the next lecture we will look into this in more details. What can cause rainfall responses outside actually a heating region in the tropical regions? We will systematically make use of this result from the Ekman pumping, because this turns out to be one of the major processes. There are other processes that we will discuss tomorrow. Tomorrow we meet again at 11. Right? So we will make use of this Ekman pumping mechanism that we have assessed today, discuss some other possible mechanisms of remote adjustment, rainfall adjustments to a localized heating or rainfall anomaly, which we could think of as an El Nino anomaly, El Nino-induced anomaly, or could be any other tropical SST-induced anomaly. We want to understand what are the rainfall adjustments likely in the tropical regions. We could also think of what is happening in the extratropical regions, actually. Could be a good exercise to think of how rainfall can be adjusted there. Oh, there is we have an exercise. But I would suggest there's a nice exercise here. Sorry to interrupt you. Just to finish. Okay, the first two are just doing some verifying things from the lecture, showing the solutions. But the exercise 3 is quite a nice one. So you should compare a numerical solution of these equations here with the analytical solutions that we have derived from the lecture. So now we go back to, we say, okay, let's say the time derivative is not 0, but we want to solve this equation in time. And this is a trick, because it turns out that this solution converges. At some point doesn't change in time anymore. So you have found the stationary solution if you integrate this in time. And you can compare that numerical solution with the analytical solution that we have found in this lecture and show, hopefully, that they are similar. And draw the Ekman spiral. It's quite useful to do that. You all have done numerical methods course, or still doing it, I don't know. So you should be able to discretize this equation and solve it, having what you have done so far already. I think it's much easier compared to all the other codes that you have done. So this is just a simple diffusion. It's just a diffusion equation with an additional term, which is this here, which gives us the spiral. But otherwise, it's just a diffusion equation. So the equation will converge to the stationary state, which is determined by setting these quantities to 0, which is the state that we have derived in this lecture. But I would say you can do this homework by next week, because from today to tomorrow is maybe too short time.